In the early part of September, Tesla unveiled a completely new energy storage platform known as the Mega Block. This innovative design is specifically engineered to dramatically reduce construction expenses for renewable energy ventures, aiming for a 40% cut. This announcement actually points to a much bigger picture concerning Tesla's overarching strategy. The company is fundamentally and aggressively redesigning how its products are conceptualized and assembled. This involves using fewer components, achieving greater integration, and implementing more intelligent manufacturing processes, all to deliver top-tier performance at a significantly lower cost. This very same philosophy is now the guiding force behind the upcoming Tesla Model 2. In our discussion today, we will dissect 3 essential methods through which Tesla is applying this cost-cutting, efficiency-driven strategy to its most economical vehicle to date. Therefore, if you appreciate clear, data-backed analyses such as this one, please consider subscribing. We are very close to reaching 10,000 members in this growing community. The central question is, how will the Fremont factory manage to eliminate 90% of the welds on the Tesla Model 2 by using a unique 3-piece assembly structure? You might not know the sheer number of welds in the car you currently drive. A typical sedan is constructed from about 400 stamped steel panels, which are then joined together by more than 6,000 spot welds. That is a truly huge number. Elon Musk recognized this issue almost a decade ahead of the rest of the automotive industry, understanding that every single weld represents a potential weak point scattered throughout the vehicle's frame. Tesla began with the Model 3, which had roughly 5,000 spot welds in its body. They then advanced to the Model Y, where they cast the entire rear frame as a single piece. This action alone slashed the weld count by over 1,600, bringing the total down to just 3,400. However, this manufacturing revolution is far from over. The truly groundbreaking aspect of Tesla's strategy lies in the far-reaching, cascading impact that weld reduction has on overall production efficiency. Every weld that is successfully eliminated saves approximately 8 seconds of robot time. This means the 2,700 welds removed from the Model Y resulted in roughly 6 hours less assembly time for each vehicle. For the Model 2's anticipated 90% reduction in welds, we are looking at a potential time saving of up to an astounding 13 hours per vehicle. This massive reduction directly and substantially impacts both the factory's production capacity and the overall labor costs involved. Now, with the new Model 2, that high number of welds is being cut by a full 90%, leaving fewer than 400 total welds in the entire car. This immense leap comes from Tesla's third-generation manufacturing process, where the Model 2 is constructed from a streamlined, standardized 3-piece design: a front mega-casting, a rear mega-casting, and the structural battery pack placed directly in between. The fundamental physics underlying this transformation clearly shows why Tesla's competitors are struggling so much to copy this innovative approach. Conventional original equipment manufacturers, OEMs, in the auto industry have intricate supply chains that are optimized for managing hundreds of smaller, individual stamped parts, each of which is typically sourced from a different collection of suppliers. Tesla's high degree of vertical integration gives them the unique ability to completely control the entire casting process in-house. They achieve this using proprietary aluminum alloys that are specially designed to maintain necessary strength, while simultaneously enabling single-piece construction. This material science breakthrough involves a unique silicon-enhanced aluminum blend. This new blend is capable of reducing casting defects by 75%, while managing to preserve the exact same structural properties that were previously achieved with multi-piece assemblies. Leaked images taken at the Fremont plant reveal a series of rear assemblies being cast entirely into a single, cohesive piece. There are no separate panels, rails, shock towers, or other components needed. These massive castings are widely believed to be produced using a colossal 50,000-ton giga casting press. This is an immense machine, powerful enough to cast both the front and rear sections of the vehicle all in one go, thereby eliminating 2,100 welds instantly. The structural battery pack is where Tesla says goodbye to another 800 welds. While established companies like Ford and GM still place their battery modules inside a separate frame and then secure that frame to the car's main body, Tesla has boldly transformed the battery itself into the car's actual floor. This eliminates nearly all 700 perimeter and crossbeam welds. To further enhance structural strength, a layer of aerospace-grade structural adhesive is applied along the edges of the battery pack. This is the same type of high-performance adhesive used to join airplane wings to fuselages, holding them together at speeds of thousands of kilometers per hour. This process of structural battery integration results in what engineers refer to as a monocoque plus design. In this design, the battery pack's function goes beyond simply storing energy. It actively contributes to the chassis' overall rigidity. The specialized adhesive bonding process uses polymers that are precisely cured at exactly 180 degrees C, creating powerful molecular bonds that are significantly stronger than traditional spot welds. This groundbreaking method increases the vehicle's torsional stiffness by an impressive 27%, while simultaneously reducing the overall vehicle weight by 12%. Compared to the conventional body-on-frame construction, the end result is a chassis that performs more like the carbon fiber monocoque of a Formula One race car than a typical car frame. When the three massive megacast pieces are finally merged together, they require a mere 16 welds. The total joining surface area is condensed into a small space of only about 0.9 mm, effectively acting like a gigantic hinge that boosts the Model 2's torsional rigidity by almost 30% compared to the Model 3. In total, this design allows Tesla to remove over 3,000 welds from this car and eliminate 90 kilograms of unnecessary dead metal. While most electric vehicles, EVs, carry between 270 and 300 kilograms of welded-together steel, which drags down both efficiency and performance, the Model 2's incredibly light 180-kilogram frame is truly in a league of its own. This weight advantage translates to approximately 30 extra miles of range per charge and dramatically cuts the 0 to 60 mph acceleration time to an impressive 2.9 seconds. Furthermore, the Model 2's frame is engineered to last for up to 30 years. This means that while owners of competitors like the Mustang Mach-E or Hyundai Ioniq 5 might have to visit the garage twice a year and potentially spend between $8,000 and $12,000 to fix rust and cracked paint around thousands of welds, Tesla owners will keep that money safely in their pockets. What aspect of Tesla's manufacturing technical breakthrough impresses you the most? If this manufacturing revolution convinces you that Tesla is fundamentally reshaping the entire industry, feel free to type megacast in the comments section below. Another important question is, how is Tesla improving the Model 2's LFP batteries through the use of a blended cathode active material? While there is much talk about new technologies like aluminum-ion and sodium-ion batteries, Tesla still sees significant potential for growth and improvement in LFP, lithium iron phosphate, technology. For the Model 2, they are focused on making LFP batteries even more reliable and efficient. Just 2 weeks ago, a substantial $4.3 billion LFP battery supply agreement was signed between Tesla and LG Energy Solution. Moreover, with its own LFP factory being established in Nevada, Tesla is taking every step possible to reduce its reliance on China. This is a critical move at a time when escalating tariffs and political uncertainties are making global supply chains riskier than they have been in years. The geopolitical significance of this shift in the supply chain goes far beyond simple cost considerations. Tesla's Nevada LFP facility acts as a crucial strategic hedge against the supply chain disruptions that have plagued the automotive sector since 2020. By bringing LFP production local, Tesla is projected to reduce shipping costs by approximately $1,200 per vehicle and shorten delivery times from a lengthy 45 days down to a mere 8 days. The factory's planned production capacity of 40 gigawatt-hours annually will be enough to power nearly 500,000 Model 2 vehicles. This represents complete supply chain independence for Tesla's most affordable car. It sends a clear message that the company is serious about rapidly expanding LFP technology for the millions of affordable cars they plan to produce in the future. By successfully avoiding the $25,000 tariff and allowing for the $7,500 federal EV credit, the final purchase price of the Model 2 could potentially drop to below $17,000 when it finally arrives at your home. However, the price is not the only important factor. To successfully balance high performance with affordability, Tesla is fundamentally reshaping the materials used inside its LFP batteries. We are about to see their patented blended cathode active material formula debut in the Model 2's LFP battery pack. While the blend is still 98% LFP, a tiny addition of 2% nickel oxide active material is included to give it an extra boost of energy. The complex chemistry behind this blended approach is a genuine breakthrough in battery engineering, a process that took Tesla's dedicated materials science team over 3 years to perfect. The inclusion of nickel oxide is not random. It is precisely engineered to occur at the nanoscale level. This process creates what researchers call heterogeneous nucleation sites, which are key to improving the mobility of lithium ions within the cathode's structure. This microscopic enhancement successfully increases the battery's power density by a notable 18% without compromising the thermal stability that inherently makes LFP batteries safer than those based on nickel-rich chemistries. With Tesla now manufacturing its own LFP cells, this small but significant change will not increase the cost to the consumer. Instead, it will bump the battery's energy density from the standard 160 to 180 watts up to a range of 190 to 210 watts. For the driver, this means the Model 2 is expected to deliver about 300 miles per charge, which is roughly 12% more range than what standard LFP packs offer. For budget-friendly EVs, this level of performance is truly unprecedented. When we consider that the BYD Dolphin barely achieves 220 miles, or the VW ID.2 reaches 240 miles, Tesla's vertical integration in battery manufacturing also unlocks cost efficiencies that are simply impossible for traditional automakers to match. While competitors are paying between $95 and $105 per kilowatt-hour for LFP cells sourced from external suppliers, Tesla's internal production cost for their blended chemistry cells is estimated at just $68 per kilowatt-hour. This cost advantage of $27 to $37 per kilowatt-hour translates to a savings of roughly $1,600 to $2,200 on a 60 kilowatt Model 2 battery pack. These substantial savings are what Tesla can either pass directly on to consumers or strategically reinvest in adding more features and capabilities to the car. Furthermore, the nickel materials used for the hybrid cathode are meticulously ground and heat-treated at around 470 F to completely burn off any impurities. This creates a cleaner final mix that actively resists degradation and extends the battery's cycle life by an impressive 30%. This means the Model 2's blended cells can retain over 90% of their capacity even after 9,000 full charge cycles at 60 POIF. Crucially, the technology and capabilities Elon Musk has brought to this car are sufficient to allow it to function as a robo-taxi or a significant revenue generator. This means that while you are sitting at home, your Model 2 could be actively out on the road ferrying passengers, potentially earning you $30,000 to $40,000 per year. It essentially pays for itself and could even generate more money than you initially spent on the car. This raises a compelling question for all of us. Do you genuinely believe that hands-off driving will fundamentally change the way we view affordable cars? If you think this will redefine driving and set it on a futuristic path, then please type hands-free in the comments. What we are witnessing is Tesla completely reshaping the very definition of a budget EV. They are using advanced casting technology that makes cars last much longer, creating batteries that boost both range and reliability, and implementing autonomy that is not just futuristic, but profoundly practical. The Tesla Model 2 is not being created to simply play catch-up with cheap imports. It is setting a completely new baseline for what everyday people should expect from their personal car. If you found this detailed breakdown valuable, please share it with someone you know who has been skeptical about the future of affordable electric vehicles. The conversation surrounding Tesla is evolving rapidly, and the more people understand what is truly happening under the hood, the better prepared they will be for the future of transportation. Thank you for watching, and please stay tuned, because the next few months are going to be absolutely pivotal for Tesla and for anyone considering going electric.